Alright, so in this video we're going to be going over right rotate for AVL trees. Last time we talked about the process of inserting into an AVL tree. So as we talked about, an AVL tree is just a binary search tree where every node in the AVL tree has the condition satisfied that both of its left and right subtrees have a height that differs by no more than 1. So what we did last time is we talked about how when you insert into an AVL tree, you need to go through and update the heights. So to do that, you keep track of the path that you take. So if we're going to add 50, we know that we take this path. You put all of those nodes in a stack, and then you walk back up the tree by popping off the stack and updating all the heights. So we know that this is 0, this is now 1, this is now 2, and this is now 3. But as you do that, you're going to also check that the AVL condition has been maintained through the insertion process. And so if we do that for this subtree, we can see that at the root node, the AVL condition breaks because its left tree has a height of 2, its right subtree has a height of 0, so the difference is 2. So now we're going to talk about what do we do once we have broken the AVL condition to fix the tree. So let's we're going to use this example for this whole video. So let's start by confirming that if we insert 5 into this tree, it's going to break at 29. So if we insert 5, we are going to walk down the tree all the way to the left because 5 is the smallest, and we're going to insert 5 here. We have to have heights, stored at each of these nodes. So before inserting 5, we know that the heights are as follows. So these are the heights of all the nodes. And so once we add 5 to the tree, we're going to walk back up the path we took and update the heights. So this is 0, this is 1, and then we'll check the AVL condition as we go. So the AVL condition is still good at 12 because 0 and -1 has a difference of 1. We're going to update this to 2. 1 and 0 have a difference of 1, so we're still good. This one becomes 3. So now we have a condition of 2 minus 0, so we can see that at 29 it breaks. And it breaks because the left subtree has a height of 2 and the right subtree has a height of 0. You can also visually see that when you insert 5, you have a left-leaning tree, so it's no longer balanced per the AVL condition. So what do we do? So in order to fix this particular imbalance of inserting 5, we do something called a right rotation. In general, a right rotation looks like this. You have a left-leaning tree, and you basically lift up L and you pull down N, and it becomes a more balanced tree. So in the condition of our example, N is 29. Yeah, 29, and then L is the node below it, which is 17, and you're just going to reverse them. Now, as you do that, all you're really doing is relinking the tree nodes. So visually, it would be like, imagine these are like hanging on a string, and you just like lift L up and goes down, but algorithmically, it just means that you're updating a bunch of left and right pointers so that the tree shifts. So first, the L node is going to maintain its connection to A, and the N node is going to maintain its connection to the C subtree. And A, B, and C are subtrees. They're not necessarily a single node, so it's just like whatever's below the point where it breaks. You're going to relink L to N. You're going to relink N to B. So B, which used to connect to L, is going to get relinked to the left of N. And then you'll also have to, relink whatever parent this whole subtree came from. So that's what a right rotation looks like abstractly. Let's actually look at what it looks like for our tree. So it's broken at 29. So in that example I just showed you, this is N on a left-leaning tree, and then ends left node we call L. What you do is you're just basically going to switch 29 and 17 and then relink everything. And so when you do that in this example, the tree becomes balanced, and you can see this is what it looks like. So the exercise we're going to go through right now is, let's actually walk through this example and see how many what actually has to be updated in order for this rotation to take place. So what is every pointer that changes as part of the rotation? So I'm going to go through and do this. So the first thing I notice is that 46 used to point to 29 and now it points to 17. So this is one pointer that's going to change. I can also see that 29 used to point to 17, but now it points to 20. So that one also changed. 29 used to point to 31, it still points to 31. 17 used to point to 17 and 17 used to point to 12 and 5, but it still does, so its left doesn't change. 17's right used to point to 20 and now it points to 29, so this also changes. You'll notice that everything above and to the other side of where it broke doesn't change. So the whole right side of the tree 46 doesn't have any changes to it at all. So what does that mean? When you perform right rotate, it actually only requires updating 3 pointers. And that isn't something that's only the case for this example that I'm showing you, but it's actually always the case, is that you only have to update 3 pointers, which is, as you know, very inexpensive because it's constant time. So here it is this one, and this one are the 3 pointers that will always get updated. So as far as rewiring the tree, it's a matter of updating the 3 pointers. But what's the other thing that you have to keep track of? Well, because it's an AVL tree, we're also keeping track of heights, right? So when you find an AVL condition is broken and you perform a right rotation, you update the 3 pointers. Do the heights of nodes A, B, and C have to be recomputed? So remember, A, B, and C are subtrees, so they have potentially lots of nodes in them, or no nodes. Do we need to go through those subtrees that we moved around and recompute their heights? Well, the answer is no. They actually don't change at all. You can see from the picture that you're just moving the A and the B and the C to a new spot, but they're always at the bottom. And since tree heights are from the bottom up, you don't have to update any of those pointers. Any of those heights. To convince ourselves of that, we're actually going to go through and prove it with one particular case. Obviously, if you wanted to formally prove this, this would not be enough, but it can at least convince us for the time being that that is true, and it is true that A, B, and C heights don't change. So we're going to start by labeling what A, B, and C are. So this is N, and this is L. And so this is the A subtree, this is the B subtree, and this is the C subtree. Then what we're going to do is we are going to write down the heights. So this is 1, or this is 0, and this is 1. This is 0, this is going to be 2, this is going to be 0. Might as well go ahead and do N as well. So N's height is going to be 3. Now remember that when you go back up the tree to update the heights and check if the AVL condition is broken, you can stop once you've found either when the height doesn't change or when the AVL condition is broken. There's no need to update the height here because you're going to rotate and fix it, and you'd have to change it again after you rotate. So after rotation, what are the heights? So we're just going to go at them This is all leaves, so those are all 0. This is going to be 1, this is going to be 1, this is going to be 2. So if we go and compare, 5's height didn't change, 20's height didn't change, 12's height didn't change, and 31's height didn't change. So this, use a different color, that means that all of the subtrees A, B, and C, none of those subtrees' heights changed. You will notice that L changed and also N changed heights, so we'll have to work through that, but we don't have to worry about updating the heights of the subtrees A, B, and C. So let's go through and actually look at what this algorithm looks like in code. So when we're coming into this right-rotate function, we have this left-leaning tree. And remember, you can only call right-rotate on this very particular case where you have an imbalanced tree that's left-leaning. And we're going to talk about in future videos the other types of rotations that'll be necessary. We are going to pass in 2 nodes. The first node is the first node that I wanted to talk about is n, and n is called n as a variable, and it's labeled n. It's the place where it breaks. And then the parent is wherever it's coming from. So the parent is n's parent. So we have a couple of conditions we're just going to check. We're going to make sure that n isn't null, and we're also going to make sure that n's left isn't null. If either of those cases are true, then you can't perform left rotate, and you probably called right rotate incorrectly. Now all we're going to do is basically set up the relink the pointers. So first, we need to define what L and B are, because those need to be updated. The pointers to those either need to be updated or those need to be moved to new spots. So L is just n's left, and then B is just L's right. So we're just going to define those as variables. And then this is just the rewiring step. So remember, we said there's 3 things that need to be changed. So n's left need to be changed, it needs to be updated, L's right needs to be changed, and then the parent needs to be changed. There's an edge case here, so the edge case is basically if the parent is null, that means that you have broken the AVL condition at the root, and so you need to update the root node instead of updating the parent. And then the other 2 cases are basically determining if n comes off the left or the right side of the parent. And so you can use the values stored at those nodes to determine if you need to update n off the parent's left or off the parent's right. And then you need to update the heights. So as we talked about, there's 2 heights to update. We need to update n and l's height. We went through that in the last slide. A, B, and C are good, but n and l both have to be updated. So the question is, in what order? So n is a child of l, so l's height depends on n. So we're going to want to update n first, and then update l's second. So that's the right rotate algorithm. So if you know where it breaks, and you know where its breaks parent, then you can just pass it in and perform based off of this algorithm. All it takes is the update of 3 pointers and changing the 2 heights. So let's actually try out the algorithm on this real tree. So remember that our tree breaks at n, and then we know that the parent is 46. So this is coming into the code, is that parent and that n. So first it's going to set up L and B. So L is n's left, so this is L, and B is L's right, so this is B. So now it's a bunch of rewiring. Instead of writing new arrows on this drawing, I'm just going to draw a new tree. So the first thing is n's left is going to point to B. So n is 29. And it says n's left is now going to point to b. So b is just one node, it's 20. So n's other node is its right node, which is c, which is 31 in this case. And that doesn't get changed because we're just changing n's left. L's right gets set to n. So L is 17. And now its right is going to point to n, which is 29. So I'm going to just draw it in another color really quick. So this is n and this is L and this is B. Kind of helps. And L's right got updated, but its left is going to stay the same. So its left is 17, is 12 and 5. Okay, what else? So now we need to update the third pointer, which is the parent. So our parent isn't a null because we didn't break at the root, so we just need to determine whether we go left or right from the parent. So L's key is 17 and the parent's key is 46. So this is true, so that means that this is going to come off the left of the parent, and so the rest of the parent's nodes are going to remain unchanged as part of this process. And then the last thing is to update the heights. So all of the heights in the tree are correct as stored, but we do need to update 29 and 17, those two nodes' heights. So in order to do that, let's write out the heights of the rest of the nodes first. So A's nodes, we already did this, were 0 and 1, B's were 0, and C's were 0. So those don't change. And then n's is going to get updated and it's going to become 1 now, based off of its left and right child. And so L's now will get updated based off of n and its left child, so this is going to become 2. If you remember from our original, that was 3 before, which is why it broke, because then 46, because its left and right tree had a greater than 1 difference. And then what you'll notice is that when we first inserted, 46 already had a height of 3, and so 46 doesn't need to be updated because we maintained that balance, and so 46, 76, and 100 will all remain the same. Okay, so that is how WriteRotate works.